So let's begin the next module, which is on perceptrons, right? And just again talk about the story so far and the story ahead, right? So now one question which I asked is like, what about non-Boolean inputs, right? So we have so far been focusing on the case where the inputs are only Boolean. So we'll have to see what happens if the Boolean inputs are not Boolean. Then the second is, in this toy examples, the Boolean functions that we are looking at so far, we were just hand coding the threshold, right? I gave you the example of the AND function, then asked you, oh, what should the threshold be? And you are able to quickly calculate in your head. Of course, you are doing some calculations, so in that case, it's not hand coded, but it's just like you worked it out by hand and you arrived at a solution. But do we always have to do that? Is it like, won't it become cumbersome in complex cases? Then the other I wouldn't say more important, but the other slightly different point here is that when we are looking at the mcculloch-pitts neuron, right, all the inputs were equal, right, and that is often not the case, right? When we make decisions, if you are making a decision based on 10 different inputs, some of them would be more important than the others. So there's always this one, like a few important things based on which might sway your decision one way or the other, while there might be many factors on which you are basing your decision. And there is no notion of importance. All the things like, is it raining, am I in the mood, is the movie is good, all of these inputs were some of given equal weights, right? And if you go back to the biological neuron, again there was this connection there, and that connection is actually the weight or the strength of the connection between two neurons. So there also it was, of all the neurons giving an input to one neuron, maybe some had more importance than the others, right? So that notion of weight or importance is not being captured. And the last is, I ended the previous video saying that could there be non-linearly separable Boolean functions, and we'll try to address that. What are these functions, and what do you do if they are not linearly separable, right? So not maybe in this particular module or video, but these are the questions that we'll try to answer over the course of this lecture. So you had this MP neuron or the mcculloch-pitts neuron, and then came this perceptron, right, which was proposed by Frank Rosenblatt. Again, we had seen this in the history around 1958. And the main differences were the following, and some of them are already obvious in the diagram itself, that earlier the inputs were only Boolean, but now the inputs could also be real. That was one difference. The other was that now you have these weights, right? So these weights could tell you which inputs are more important than the others. And there's also, now that you have these weights, there's also a mechanism or a learning algorithm to learn these weights, right? So you might vaguely have an idea of which inputs are important, which are not, but typically you would want to learn this from data. And in the past, maybe while making decisions, I have given more importance to who is the actor in the movie as opposed to who is the director in the movie, right? So maybe these things you want to learn from data. So these weights are now learnable, right? So you have, and we're going to look at a learning algorithm for learning these weights. So like three main differences. Now you have weights. The inputs are no longer Boolean. You could have real inputs. So that was one action item that we had, and we have taken care of that in this model. And the third is a learning algorithm. So far we were talking about hard coding or like mentally calculating what the threshold is. But now we'll look at a good learning algorithm for learning the weights, right? So what we're going to learn in this course is not the original perceptron or the classical perceptron model, but more the perceptron model which was later refined and analyzed by Minsky and Papert. Again, we had referred to this in the history in 1969. So that's the model that we're going to be talking about. It's just to make it clear that what we are talking about. Okay. So let's go ahead, right? So what does the perceptron model look like? So it's very similar, right, in form at least. So you have y is equal to 1 if the weighted sum of the inputs is going to be greater than or equal to threshold, right? So earlier, in the mcculloch-pitts neuron or the MP neuron, there was no notion of weights. So it was just that if the sum of the inputs is greater than or equal to threshold. But now I have if the weighted sum of the inputs is greater than or equal to threshold, and that's where I get to assign weights to inputs. So if the input value is small, but if the weight to the input is large, then still the contribution would be higher, right? And notice that this index is over 1 to n because there are n inputs. So from the first input to the last input, right? So 1 to n, that's where the indices are coming from. and it is going to be 0 if this weighted sum is less than threshold, right. So again, a very similar form to the MP neuron. Now on the rest of the slide, I'm just going to do some rewriting to arrive at a more neater form, right. I don't want to keep writing this. Let's see where I reach there. So if I rewrite the above, I'm just going to take theta on one side. So I have this minus theta greater than or equal to 0, nothing wrong with this, and minus theta less than 0, right. So I've just taken theta on one side. Now something interesting will happen. So now the theta has disappeared. Looks like the theta has disappeared, but actually it hasn't, because I've added this I equal to 0, right. So what I'm saying now is that my sum earlier was w1 x1 plus w2 x2 plus blah 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 up to minus theta greater than or equal to 0, right. That's what this equation was saying. Now I am starting from w0, right, because it's I equal to 0. So I have w0 x0 plus all of this, and then the theta is disappeared, right. There's no theta in this equation. So what have I done actually? All I'm saying is that I'm going to have an imaginary input x0 which is equal to 1, and then another weight w0 which is actually equal to minus theta. So if I substitute these values, then these two inequalities become the same, right. If I make w0 as minus theta and x0 as 1, then I just get minus theta as the first term of this sum of terms, and then that these two inequalities that I have here, right. So as I said, this was same and then greater than or equal to 0. So these two inequalities become 0. So it's a simple change which I have made quite obvious. And what it means is that I have this extra input which is x0 equal to 1 and w0 is actually minus theta. And so now the inequality falls in place. So now my summation is from 0 to n with the understanding that x0 is 1 and w0 is minus theta, which is the same as saying summation 1 to n minus theta, right. That's what my original inequality is, where I started from. So this just makes it neater in some sense. I have no theta now. Now the theta has become w0 or minus w0. Okay. So we'll now try to answer the following questions, right. Why are we trying to implement Boolean functions, right. So why am I talking about Boolean functions so much? I said that we can implement real functions, but still for the large part of this lecture, I'm going to focus on Boolean functions. So I'll tell you why I'm focusing on Boolean functions. The second is why do we need weights, and why is this w0 called the bias, right. So these are some very, I would say, heterogeneous set of questions that I'm going to try to answer, right. So first, why are we talking about Boolean functions? So let's take the simple thing of task of predicting whether we would like to go for a movie or not, or whether we like a movie or not, right. And this decision might depend on several factors, like who is the actor of the movie, who is the director of the movie, what's the genre of the movie, and all of this you could convert to Boolean inputs, right. Is actor Matt Damon? Is actor Christian Bale? Is genre thriller? Right? Is genre comedy? Is director Nolan? And so on, right. So you could just convert it into these series of Boolean inputs, right. So many real world problems, you could just try to convert them to problems where the inputs are Boolean and the output is of course Boolean, right. Whether you are going to watch the movie, or whether you want to watch the movie, whether you are going to like the movie, and so on, right. And now based on the past viewing experience, now that this model has weights, we could learn the weights from some data. How we are going to learn that is not clear yet, right. And it's going to take a series of lectures to understand that in a much broader context. We will do it in the context of perceptrons soon, but the broader context would get clear over a series of lectures, right. So this is something that we would like to learn, and now this model has these placeholders for weights which could potentially be learned, right. And these weights could be such that, what do we want, right? We want the weighted sum to be greater than some threshold, right? Or the weighted sum including the threshold to be greater than or equal to 0. That's what we want, right? So now you could imagine that there is an input signal which is weak, but the weight for that input signal is so high that collectively it crosses the border, right? And so it's possible that you only have one input which is on, right? Which is the director is Nolan, and all the other inputs are off, but the weight of this input might be very high based on your data, because you have always liked movies directed by Christopher Nolan. So you would have a very high weight for this, and because the weight is high, even though there is only one input which is on, the weighted sum might still cross the threshold, right? And that's what the weights help you, and that's the notion of importance encoded in an inequality, right? So that's where the weights are helping, right? Now coming to the bias, why is W naught called the bias? So W naught actually refers to the prior or the prejudice, right? So what's the role that it is playing, right? It is one of the terms in the summation, and it's like the blockage, right? So if W naught or if theta is a very high value, right? So then your sum has started off with a very low value. It's a high negative value that you have started off, and now to cross this so that your total weighted sum is greater than 0, all of these inputs will have to contribute a lot, right? That means many inputs may have to be on, or many high weighted inputs have to be on, right? So this theta is telling you that what is your inertia for crossing the border, right? So if you are a very niche moviegoer who only watches movies which have Matt Damon, which are thriller and which are directed by Christopher Nolan, right? Then your theta, let's assume all the weights are 1, then your theta would be -3. And only if these 3 inputs are on, then you will have minus theta, which is -3, plus the actor is Damon, plus the genre is thriller, plus the director is Nolan, and then this would be greater than or equal to 0, and only then you will go and watch the movies. If any of these inputs is not on, right, if either the actor is not what you're looking for, then you will not go to watch. So this is the bias, right? This is what it tells you about that specific user, and hence it's called the prior or the bias, right? But if you are like a movie buff who does not care about who the director, actor, director is, right, then in that case your threshold could be 0. And even if none of these criteria match, the actor is not Matt Damon, the director is not Nolan, the genre is not thriller, still you will cross the threshold, right? And still you will go and watch the movie because you are just a movie buff. So this threshold is trying to encode the initial bias that you have, right? And it could be adjusted to reflect whether this person is a movie buff or not, right? In other situations, it could be reflected to, it could be adjusted to reflect the prior, as we say, right? So what is the, without knowing the data, without knowing the inputs, what is the prior that is about you taking this decision as a positive versus negative, right? 0 versus 1. So that's why it's called the prejudice, and the same thing I've explained on the slides. You can go back and read it later, right? Okay. So now coming to the question, so this was to motivate a few things, right? That why are we interested in Boolean functions? Because many real world problems you can map it to Boolean functions. Then why do we have weights? Because in many real world problems you want weighted inputs, you want certain inputs to be more important than the others. And what is theta, what is the prior? So that has also been explained, right? Now let's move on to a different set of questions. So what kind of functions can be implemented using the perceptron, right? We know the answer for the mcculloch-pitts neuron. It can only be used to implement Boolean functions which are linearly separable. That means you can draw a line and all inputs which have a positive output will lie on one side and all inputs which have a negative output will lie on the other side. So is the perceptron any different, or what kind of functions can it be used? So if you look at the mathematical form of these two, there's only the red part is different, right? So earlier you had summation xi greater than or equal to 0, now you have summation wi xi greater than or equal to 0. So in essence, both of these are actually finding linear boundaries, right? It's just that now you have certain coefficients for your inputs, right? So that's what is happening here. It should be clear that even for a perceptron, you're just learning a line, and then you will have some points which lie in the positive half space of the line, and for those points the output would be 1, and some points which lie in the negative half space of the line, and for those points the output would be 0. So just in case this is not very clear, we'll look at an example and it will become clear. But then the question which already comes up is that if it's not different, if it's also learning a decision boundary, then what's linear decision boundary, then what's the difference? The difference is that now we have weights and we also have a learning algorithm for learning those weights, right? So we are slowly moving in the territory of learning with the perceptron, and we'll go deeper in this territory as we go to sigmoid neurons and then eventually to deep neural networks, right? So that's where we are slowly making a transition to, right? So let us first revisit some Boolean functions to convince ourselves that this is actually drawing a linear decision boundary only, right? So you have the OR function. I know what the OR function looks like. And now in terms of the perceptron, what does it mean? This is what my perceptron function is, right? So I'm going to take a weighted sum of the two inputs plus W naught, and I want that to be less than 0 in this case, right? I want that to be greater than or equal to 0 in this case, greater than or equal to 0 in this case, greater than or equal to 0 in this case, because that's how my OR function is, right? Now let me just expand this, right. So what is this first guy is telling? W0 plus W1 into 0 plus W2 into 0 should be less than 0, which implies that W0 should be less than 0. Similarly, the second equation is saying W0 plus W1 into 0 plus W2 into 1 should be greater than or equal to 0, which is just saying that W2 should be greater than or equal to minus W0, right. Similarly, the third equation is, this is what it implies, and similarly this is what the fourth equation implies, right. So I'll just take a pause for 10 seconds here so that you could just look at the equations and convince yourselves that this is indeed the case. Okay. Now this is not equations, inequalities. So these are the 4 inequalities given to me, right. And now I could just try different values of W1 and W2 and W0 and try to figure out one combination of W1, W2, W0 which satisfies these inequalities. Of course, in practice, I would not like to do this randomly, but have a learning algorithm which does it, and we'll go there. We'll go to the Perceptron learning algorithm. But for now, it's okay if I just think a bit about it, and I've already thought about it, and this is a set of values which I'm going to give you. If W0 equal to 1, so not 1, sorry, this should have been minus 1, right. So this should have been minus 1. So if W0 equal to minus 1, if W1 equal to 1.1 and W2 equal to 1.1, then all these equations are satisfied. You can just plug in these values and see that all the 4 inequalities are satisfied, right. And now I'll look at the geometric interpretation of that. So what is the geometric interpretation? I'm saying that minus 1, okay, plus 1.1 into x1 plus 1.1 into x2 greater than or equal to 0. This is the positive half space. Less than 0, this is the negative half space. So look at the line equal to 0. That's the separating line which is separating my inputs into this positive and negative half space, right. So let's see what that line is looking like. So here I have this line. So this is the line minus 1 plus 1.1 x1 plus 1.1 x2 equal to 0. As I had said earlier, this is minus 1, right. So this I'd already mentioned. So that's why this is minus 1 here. Okay. Oh, it's already deleted. Okay. So now what is happening here, right? So the green shaded region is actually the positive half space of the line. All the points in this half space will satisfy the equation minus 1 plus 1.1 x1 plus 1.1 x2 greater than or equal to 0. They will satisfy that inequality, hence there is a positive half space. And all the points which are in the red zone, and in my Boolean world there is only one such point which is 0, 0. So that is going to lie in the negative half space, and that's exactly what we wanted, right? So this is a correct solution. Of course, this is not the only correct solution. So I'll go ahead and I'll go ahead and change this a bit. So I've changed this. This is also a valid solution, right? Because again, my green region has the positive points. This is not a valid solution, and you can see here the error is 2. Why is the error 2? Because this is the one point which lies in the positive half space, and it rightly lies in the positive half space. There are 3 points which lie in the negative half space, of which actually only one should have lied. The red point should have lied in the negative half space, but there are these 2 green points which are also lying in negative half space. So I'm making errors on 2 inputs. So in this configuration, my perceptron is not actually representing the OR function. It's not implementing the OR function because it is making errors, right? So this is not an implementation of the OR function, but there could be other values. This I already showed. I could even adjust the threshold, right? So this W0 actually in the terms of a line tells me what my y-intercept is going to be, right? So I'm going to adjust it, and it will intersect or intercept the y-axis at different points, right? And now so far the error is 0, so all these solutions are valid. But now if I come here, then I have a problem. You can see error is equal to 1, because one point, red point, which should have been in the negative half space, is now lying in the positive half space, right? So now my learning algorithm should be such that it should draw the line in a way that my negative points are on one side and the positive points, or the points which give a negative output are on one side and the positive output on the other side, right? So that's what we would want from the Perceptron algorithm. And this same thing, right, where I have put in these, tried to substitute the values and then come up with inequalities and then just hand solve for the inequalities. The same thing you could have done for the mcculloch-pitts neuron. There you would have had only W0, right? There was no W1 and W2. So you would have come up with 4 sets of inequalities and only one variable, which is theta or W0, and then you could have tried to find the value of that theta. So you can go home and try this, try to write the 4 inequalities for the mcculloch-pitts neuron. Remember, there will be no W1, W2, and then just see if you can come up with the right value of theta. So that is also doable, right? So the idea of learning is, or finding the right value for the parameters, is not something that we have come to suddenly. I'm just saying that we had already done it in the case of the MP neuron also, where we had tried to find this value of theta. It's just that there it was very obvious what the value of theta should be, whereas here it could be a bit difficult, right? And we'll have a learning algorithm to do that. So I'll end this module here, and when we come back, I'm going to talk about errors and error surfaces.